Cool. Morning, everyone. For those of you who don't know me, my name's Sashin, and today I'm going to be sharing the secrets of how to predict the future. So, to predict the future, we've got to look at our possible options. So recently at work, we were discussing a popular video going around where a man describes that the Rubik's Cube has been solved faster and faster every year since it came out. And it won't be long until they can solve the Rubik's Cube in negative time, which would allow us to travel back in time using the Rubik's Cube. And this was a little bit of a joke at work, and we said that we had already completed last week's work next week, but we also labeled it the negative time theory. So when it comes to predicting random numbers generated by a computer, this is one of our possible options. So you could run the function, we could get the output, and then use the negative time theory to travel back in time, and then we would know what the output would be. But that would be the easy option. So there's a harder option called fancy algorithms. And I'll leave the easy option for you guys to try at home, and we'll take a look at the fancy algorithms option. So for us to firstly understand what randomness is, I'll pull up Wikipedia here. And it says randomness is the apparent or actual lack of a definite pattern or predictability in information. So what that basically boils down to is that there's no way to predict the outcome beforehand. And if you look at something like a coin toss, for example, where there's multiple factors that could affect it, like the wind drift, the force, or the air resistance, there's no accurate way to predict which side the coin would land on. But if you had accurate values for each of these initial conditions, then you could, with high probability, predict the outcome of which side the coin would land on. And what that basically means is that if you know the initial conditions to a chaotic system, you can model the outcome because it's deterministic. So randomness is then basically our ignorance to the initial conditions of a chaotic system. Computers themselves are actually deterministic machines, which means that the numbers that they generate aren't truly random, and they use something called pseudo-RNGs, or random number generators. And the way those works are the algorithm takes in some initial value, and that's called a seed, and that's used to generate a sequence of the next values. The sequence of next values have some sort of repeatability factor to them, and we call that the period. And the greater the period, the greater the algorithm is. And this could be useful in things like playing games where you want to spawn characters in random locations, but it wouldn't be so great in things like cryptography because predictability isn't appreciated much in that field. So what are we actually trying to break today? Well, there's a built-in function with JavaScript called math.random. Comes with almost all JavaScript engines. And it's a function that returns a floating point pseudo-random number that's greater than or equal to 0 or less than 1. So Node.js in Chrome uses an engine called V8, and that's maintained by Google, and it's open source, so you can actually take a look at their code on GitHub. And let's actually do that. So if you go and look at the implementation of the math.random function, you'll see that they're using an algorithm called the XOR shift 128 algorithm. And the way it works is it's two initial state values there that it takes in. State 1 becomes state 0, and state 0 becomes state 1 after all the shifting and XORing that's happening there. It's a little bit of a complicated algorithm, but lucky for us, we don't really need to understand it because we have a cool tool on our side called Z3. So Z3 is an SMT solver. To write this down, it's a satisfiability modulo theory solver. And the way Z3 works is that you define some initial problem in the form of an equation to it, and then you provide some constraints to it, and then Z3 will give you an answer back in return. So our goal today will be to find the initial state values for the XOR shift 128 algorithm, and we can use that to get the random number out of it. So let's go ahead and take a look at that. Let's grab this. So what I'm going to do is generate 5 random numbers here using math.random. And these are 5 initial random numbers. And we'll use this as a sequence to feed to Z3 to try and solve for the next one. So that's our initial sequence. Here we define our state 0 and our state 1 using Z3 bit vectors as our unknowns. And here we emulate what's happening in that XOR shift 128 algorithm we saw a bit earlier. And down here, you'll see that we're getting something called the mantissa to try and get the value between 1 and 0. So to understand what the mantissa is, we have to look at how the IEEE 754 standard tells us to represent numbers on computers. So the 64-bit number is represented with 1 bit as a sign, 11 bits for the exponent, and then 52 for this part they call the mantissa. And then when you want to get the actual number it represents, you can take the sign times by 2 to the power of the exponent times by the mantissa. So that's what we're doing over here to get the mantissa, and that's our random number. And we ask the tree to try to find one that matches. When it does match it, it does something where we get this first state and it converts it to a double function, which is also found in the V8 library. So let's go ahead and run this. So our predicted value is 0.286533, very long number. And we can pull up here the other console and type math.random. And that's the next number that it generated. So we could continue doing this and keep getting the next number. I see Kenneth can't see in the front there, so I'll zoom in for him. And that is how you can predict random numbers. But then the question becomes, well, how do we achieve a randomness then? And the answer to that is lava lamps. So if you look at less predictable environmental factors, things like the flow of lava or atmospheric noise, you can use that as a source of randomness because it's not easily predicted by us. Lava Land is a system that Cloudflare uses where they have a wall full of lava lamps and an input camera pointing towards it, and they use that as a source of randomness for their production servers. Yeah, that's pretty much my talk. I hope you guys enjoyed it. Thank you.